Hello, Calc. You're viewing this on Tuesday after class, and that's the 21st. And let's see, 37 years ago, I was having my first baby boy, second baby, but first boy, and his name was Brian. All right, all that aside, I am going to go back into numerical integration. All right, numerical integration is another way of saying Riemann sums, and that's just where we're breaking down a situation into smaller pieces. The area under the curve broken down into smaller pieces and adding up the area of each. So what we've been doing is summarized with this picture. Suppose I have a function and I want the area under that function between here and say here. So say I want 4 sub-intervals, and I'm going to do, say, lower sums, or you could call them right boxes. Sometimes they call them inscribed. So remember in your geometry days, an inscribed triangle like that, the vertices were on inside of the figure. Well, these are also called inscribed rectangles. And so that's another way of describing it. But notice it's not going to get the entire area under the curve, because this part that I'm darkening will not be included. Say I'm going to here. So what about then doing the other way? Or what if we just, as I indicated, what if we increase the number of subintervals? So 1, 2, 3, 4, 5, 6, 7, 8. And I'll do upper ones this time. Just 2 upper ones, in this case, are also right ones, and they're called circumscribed rectangles. So that's another name you might run into. And this time the part above, say I'm going to here. So the area under the curve from this line to this line is going to be approximated by these rectangles, but it's going to be greater by the part that's shaded in. But it looks like less of error than was under the curve, here shaded in. So the point being is, what happens if n goes to infinity? The number of rectangles becomes infinite. Then we would have the limit as n approaches infinity of some Riemann sum, and that would be the exact area under the curve. So let's look at that a little closer here. So how can I, with algebra, depict this Riemann sum? Well, I'm going to use an old friend of ours, the summation symbol, and I'm going to start with a counter. I'll call it I, and I is going to start at 1 and go to n. And what am I going to multiply to get the area for each of these rectangles? Well, one thing I'm going to have is the width of the subinterval. So I'll call that change in x. And then I'm going to have the height of the subinterval. And I'm going to call that f of change of x sub I. So what I mean by that is, say we're talking about this one. This would be x sub O, this value. This value would be x sub 1, x sub 2, x sub 3, and x sub 4. So do you see how I can use this notation, and the first time through it'll grab f of change of x times 1. So that means it's going to grab this one. It's going to get the height there because it's throwing it into the f function. So change of x 1 time, then change of x 2 times, 3 times, 4 times. So it will be getting those values. So when it's right boxes, it will be grabbing change of x times f of x1, change of x times f of x2, and so on. All right, and then as we mentioned, the limit of those as n approaches infinity will be the exact area under the curve, no approximation needed. All right, so we're going to look at some summations that come up a lot in our work. And this comes from when we talked about infinite sequences and series. So let's see what we can drag from our memories. I equals the summation from 1 to n. Now we just talked about that. What if I have a constant, and that constant there's no I in the term at all. So it's just a constant. So an example of that would be summation as I goes from 1 to 5 of, say, 3. So what does that mean? Well, when I is 1, we get a 3. And then this is a summation, so we're going to add it. So then I increments by 1 to 2. And then what happens when I is 2? We get 3 again. What about when I is 3? When I is 4? And lastly, when I is 5. So do you see, we added 3 5 times, and we got 15. So that will happen no matter what constant we have, and it's always going to be that constant plus itself, plus itself, plus itself n times, which will equal n times c. Alright, so if ever this comes up in our work, something like this, remember that we can use these expressions. Alright, the second one is more from memory or from those mathematicians who figured it out for us. Alright, write down what you think that summation looks like. So we're going to get when I equals 1, then it's going to increment to I equals 2, 3, 4, all the way up to whatever n is. Now there was a time when we looked at that, we looked at all of those, and we actually wrote them out. Like 1 would give us 1, then the next one would give us 3, and the next one would give us 6, and the next one would give us 10, etc. And we would come up with a general term where this is the first term, this is the second, this is the third, this is the fourth. And we had to come up with what we called a general term that always worked. So what could I do to 1 to get 1, and the same thing to 2 to get 3, and the same thing to 3 to get 6. And some of them were tricky, and it turned out that this one was kind of tricky. And it turned out it was going to be, the whole summation was going to be n times n plus 1 over 2. So let's go and see if that works. Let's say we're going to add up the first 12 terms. So we'll see if that works. So we have 1 plus 2 plus 3 plus 4 plus blah 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 up to 12. And I got 78 when I just did that on my calculator straightforwardly. And now I'm going to try it in with that formula. So n, we're going from 1 to 12, so n is 12. So we're going to get 12 times 12 plus 1 over 2. which ends up being 6 times 13, which is 78. 78. So it worked at least for one example, and you will find that it works for all. So write that down. This summation can always be written like that. So I'll give you the next two with no further ado. I squared, which means we're having 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., up to whatever n squared is. And someone along the line noticed this pattern. N times n plus 1 times 2n plus 1 over 6. It always works. So if we end up with a summation of a value squared, we can substitute this in for it. So, and I don't think our work will reflect more than the cubed value. So the summation as I goes from 1 to n of I cubed, which means 1 cubed plus 2 cubed plus 3 cubed up to n cubed. And someone noticed it was n squared times n plus 1 quantity squared over 4. Who would have thought? I'm sure we could do it if we had given ourselves half a chance. All right, so keep these in mind because they will come up. All right, I'm going to shut down this preliminary portion and get to the meat of the matter on part 2. So see you in a few.